Hello, welcome everybody. This is lesson S5 on radio and optical telescopes. First thing we're going to just quickly do is we've got two videos actually with this lesson. This is just the teacher notes one. First thing we're going to do is we're going to define the word telescope. That word telescope is basically a device to magnify celestial bodies. Now we've got two main types, which is what the other video is mostly about. The first one is the reflective. Now with the reflective, you've got an eyepiece up at the front usually. Big long tube. We've got a concave mirror here, secondary mirror here, so light's going to shine in, bounce off the mirror, bounce this way and towards the eye. Second one is the reflective, which is basically going to have two lenses working together in one big long tube. Now Galileo was the first one. Actually before we do that, page 370 is a good place for you to go if you want better diagrams of these. Now Galileo, he was the first one to really record some significant observations through a telescope. He was not the person who discovered it, but he observed the moon's blemishes, which had shadows that lengthened and shortened with the sun's angle on them. Now, with that, Galileo concluded the moon's surface must have different mountains and craters on it. Now, another thing he observed is that the sun had spots on it. Over a period of about a month, the spots, they actually moved across the surface, disappeared, and then reappeared again on the other edge. So he concluded that the sun rotated on its axis from that observation. So the idea here is that one day the sunspot is here, and over the course of a month, over the course of a month, that sunspot actually moves across, boop, 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 disappears, and then all of a sudden reappears on the other side and comes across again. Okay. Now, when viewing celestial bodies, he was able to observe the planets within some detail. However, the stars were still pinpoint in appearance, and so he basically concluded that they must be much further away. Than the planets. That was one thing that was a little bit of just a conclusion based on his, shall we say, his presuppositions. Turned out to be right, but anyway, Jupiter was accompanied by 4 small stars that moved back and forth across it. And so what he did is he essentially figured that these 4 stars were actually 4 moons. Now, they are the largest of the 4 moons, but he observed that. Now, this really meant that apparently not everything revolved around the Earth after all. With modern telescopes, scientists found that Jupiter actually has 17 plus moons. Just kind of one of those things. Now, a radio engineer, an amateur astronomer, actually built a radio dish in order to actually listen to the sky. So he was a radio engineer, and he decided, hey, I'm going to actually listen to this. Now, let's put in the word listen. To the sky. Now, during the 1930s, now he discovered that there were particular places in the sky he thought there must be some radio objects in space that were responsible for those emissions. Now, radio dishes can actually penetrate dust clouds in the galaxy where visible light stops. Now, just the same way that you can hear a radio through your house, even though light cannot enter in through the walls, the radio signals can, the light can't. Same type of idea here. The radio waves can actually penetrate these dust clouds, things that we can't actually see. Now, computers store the data, and they actually will false color these in order to generate images. And radio astronomers, they want to identify these things. They're strong radio signals with ones that they've actually observed before with optical telescopes. And so the idea is that if you've actually seen something and then somewhere else you can get a radio signal that matches, then it must be the same type of object, even though you can't actually see it. Now, improvements in computers and precision and modern clocks have enabled these these radio telescopes to connect them. Connect telescopes without wires. And what that does is it creates a very long baseline interferometry. Interferometry. And these produce images that are hundreds of times more detailed. The idea behind this is that if I've got a telescope over here in the world and another one over here in the world looking at this object, I can see it from both here and here and get a big angle. That's supposed to be a straight line. But that's basically the idea. I want to just take a look at some of your textbook questions actually have this formula in them, and so I just wanted to highlight this a little bit. It's just a formula. It's not one that you need to memorize, but a couple of questions do have it. So if in this case here the magnification is 75 times, the focal length is what we're looking for. The focal length of the objective, and we know that the eyepiece is 2.5. We're going to just do some algebra here. 75 times 2.5 will get us that focal length. And so when we multiply that out, we get 187.5. Centimeters, because this was in centimeters, and so that will be your focal length of your objective. And the questions 4 and 5 in the textbook just operate on the same formula. Okay, hope that helps. Thanks for watching.